Hello all, I am creating this video for my evolutionary algorithm final project. It is completed in pair by Ayushi and my classmate Ajay. It is for the submission of evolutionary computing and humanoid robotics code CS6271. Moving to the next slide, the content. It is basically divided into 10 to 11 parts as shown. First, introduction. Second, data handling. Third, data splitting. Fourth, grammatical evolution. Fifth, evolutionary computation with grapes. Grammar use, grammatical evolutionary parameter, fitness function, reference and tool, insight and conclusion, future directions. Introduction. Symbolic regression plays a crucial role in understanding complex data. So, we are using symbolic regression for solving the complex data. The objective of this project was to apply genetic programming specifically using grapes. Grapes grammatical algorithm in Python for evolution. There are basically domains of graphs three: party, regression, classification. The analysts focus on exploring the characteristics of the evolved expression and predictive performance on the data set. We have two data sets, which is train and test, which will be explained in further slide. Data handling. The very first step involved in loading and pre-processing the dataset. The training and test dataset containing information related to incoming were loaded using Panda library. Using Panda's library for the loading of the data and training set is done. Panda function for analyzing, cleaning, exploring and manipulating data in dataset. Extensive pre-processing was conducted, including one-shot encoding of categorical feature and numerical transformation of specific column. This meticulous data preparation was crucial for feeding into the symbolic regression. The quality of input data signifies impact the model ability to discover accurate relationship in the data. Data splitting. The training dataset was partitioned into feature X train and target label Y train. This separation was essential for training the symbolic regression model. The file used are in the CV format and read by using pd.read function for the pandas library as shown. We use test dataset to check whether the system is trained well or not. It serves several important purposes such as model evolution, preventing overfitting, assessing generalization, hyperparameter tuning, and avoiding data leakage. Splitting data into two datasets enhance algorithm outcome and performance. The trained data gives feedback to the algorithm, whereas the test data gives feedback to the user. Moving to the next slide, talking about grammatical evolution, I got this picture from the lecture provided by our professor. In this, we combine the grammar, fitness function, search engine in the grammatical evolution and get the solution. For grammar, we have used the grammar file in the project. It is mounted from the drive and file we used in the grammar, my grammar file format. The fitness function is further discussed in the upcoming slides. And for the search engine, we have used deep grammar. The grammar is divided into two parts, that is Boolean feature and non-Boolean feature. In this project, we display the training dataset and check which parameter has only two input is classified into Boolean dataset, like sex having only male and female, native country which has United States and other is considered as Boolean, whereas entries such as work class, education, marital status, relationship, race has multiple input, so it is non-Boolean. We have divided this using the grammar which divides the dataset into Boolean and non-Boolean. Here, the x of 1, 4, 6, 8, 9, 10, 11 and so on are the Boolean features which have only two input, whereas others like 0, 2, 3, 5, 7 are non-Boolean. and they do not have more than two values. The grammatical evolution parameters. These are parameters used with corresponding values. Population size 1500. It is the number of individual potential solution or genome in each generation of the population. Max generation 150. Maximum number of generation algorithm which goes through. P crossover 9. Probability of crossover, that is recombination occurring between two individuals during reproduction. P mutation is equal to 0.02. Probability of mutation occurring in an individual during reproduction. Elite size 5 is the number of top forming individuals that are preserved for one generation to next. Hall of Fame size 5. Number of best individual recorded over the entire evolutionary process. Tournament size. Number of individual randomly selected to complete in tournament for reproduction. We have two selection technique, tournament and roulette wheel, but we have used tournament in this. Next, random seed 42. Seed for random number of generation. Consumption lazy. The value lazy suggests a particular mode of consumption. Genome representation list. List implies that genome are represented as list. Next is max initial tree depth 13. Maximum length allowed has no max genome length none. It means maximum length allowed has no restriction. Next, the maximum depth of the initial tree is defined 13. The minimum initial depth is 3, where as the maximum depth are allowed for the tree is 90. Max wrap 0. Maximum wrap allowed for genome during evolution. Codon size. It is genetic information unit set to 255. These parameter collectively defines the configuration of evolutionary algorithm potential used for symbolic regression or another optimization task. Altogether gives us the result of best individual and best fitness.
Hey all, this is Ajay. I'll be continuing the explanation for further slides. Starting off with the parameters used in the grammatical evolution algorithm. They're basically used to control various aspects of the evolutionary process. Starting with population size. It defines the number of individuals in each generation of the population. A larger population size can help explore a larger search space, but this process may also increase computational cost. Max generations. It sets the maximum number of generations the evolutionary algorithm will run. This helps limit the computational time. Crossover. Probability of crossover or recombination between the two individuals is nothing but a genetic operator that combines two genetic information from two parents to create new individuals. A higher probability encourages exploration. Mutation. Probability of mutation introduces small random changes in individuals to promote exploration. A lower probability ensures that the population doesn't converge too quickly. Elite size. The number of best individuals to automatically carry over to the next generation without undergoing genetic operations like crossover and mutation. It helps to preserve good solutions. Hall of Fame size. The number of best individuals to be recorded in the Hall of Fame. The Hall of Fame keeps track of the best solutions found throughout the evolutionary process. Tournament size. This is the size of the tournament selection. Tournament selection is nothing but a mechanism for selecting individuals based on their fitness. A large tournament size increases selection pressure. Random seed. Setting a random seed ensures reproducibility. The same seed will produce the same sequence of random numbers, making experiments reproducible. Codon consumption. It specifies how codons, that is, genetic informations, are consumed during the decoding process. Lazy consumption typically means that unused codons are ignored, allowing for more flexibility in genome length. Genome representation. It defines how the individual's genome is represented. List representation is a common choice where the genome is represented as a list of elements. Max genome length. The maximum allowed length of an individual's genome. If none, there is no limit. It controls the size of the solution. Max init tree depth. The maximum initial depth of an expression tree is when individuals are created. A deeper tree are for more complex solutions. Min tree depth. The minimum initial depth of an expression tree. A shallow tree provides simpler initial solutions. Max tree depth. The maximum depth of a tree can reach during the evolutionary process. It helps control the complexity of evolved solutions. Max wraps. The maximum number of times a non-terminal symbol can be replaced during an expression. It helps to prevent infinite looping. Codon size. The size of the codons in bits. It determines the granularity of genetic information. These values were chosen based on a combination of factors, including the nature of the problem, available computational resources, and empirical experimentation to find a balance between exploration and exploitation. The values are not fixed and might require tuning based on the specific characteristics of problem at hand. Evolutionary computation with Grape. Our decision to harness Grape's genetic programming module stemmed from its proven efficiency in tackling the intricacies of symbolic regression tasks. This meticulous approach guided our choice with careful consideration given to crucial factors such as population size, crossover and mutation probabilities, and the composition of elite individuals within the evolving populations. These decisions were akin to tuning the parameters very finely. It is like tuning a radio to get its best signal. As our algorithms evolved, they gave us a special code, a symbolic expression that's like a secret formula behind predicting incomes. The star performer of our best algorithm not only rocked the fitness score but also gave us a sneak peek into its personality, showing us its traits like how deep it thinks and what is its genetic makeup. It is like finding a superhero in the world of algorithms, revealing how it cracks the code of predicting incomes. Now, moving on to fitness function. This function evaluates the performance of an individual in the evolutionary process by comparing its predicted outcomes to actual outcomes. The goal here is to minimize the fitness value, which is a measure to how well the individual's prediction align with the true outcomes. This function handles potential error during the evaluation process, such as floating point errors, zero divisions, overflows, and memory errors. If an individual is deemed invalid due to the errors in generated phenotypes, the function returns a fitness value of nan, which is not a number, effectively penalizing it. Now, within the try block, the function calculates the element-wise equality, which is compare between the true outcomes and the predicted outcomes. It then computes the mean of the binary comparisons, subtract it from 1, and then assigns the result to the variable fitness. The higher the fitness value, the worse the individual prediction match the true outcomes. This fitness function focuses on accuracy, aiming to minimize prediction errors in the context of classification task. References and tools. In this project, we have made extensive use of few Python libraries, including pandas for data handling, numpy for numerical operations, matplotlib for visualization, and the grape library, serving as the core for genetic programming, which played a vital role in evolving symbolic expressions. Prediction and results. In this task, a symbolic expression was evolved using grammatical evolution to predict income classes on a test dataset. The evolved expression was then applied to the test data and performed performance metrics such as accuracy, precision, recall, and F1 score were computed to access the model's predictive capabilities. The analysis of these metrics provided insights into effectiveness of the evolved symbolic expressions for predicting income classes. Insights and conclusions. The code effectively presents key attributes for the best individual evolved through grammatical evolution, including the symbolic expressions, fitness, depth, and genome details. This insights into the complexity of the evolved solution, which is valuable for understanding the algorithm's performance. Acknowledging the project limitations as well, highlighting potential areas for improvement. I would suggest exploring alternative evolutionary algorithms and fine tuning parameters into enhanced performance. This recognition underscores the iterative nature of the project, with opportunities for refinement and further research. Summarizing it, the code provides valuable insights into the solution's characteristics while acknowledging its limitation. The conclusions encourages future exploration through alternative algorithms and parameter adjustments, emphasizing a continuous effort for refinement and improvement in the project. This project serves as a foundation for ongoing exploration and enhancement. Potential future directions include investigating alternative grammars, which could entail refining the rules guiding the evolutionary process. Additionally, experimenting with various selection mechanisms in genetic programming, such as ways of choosing individual for reproduction, offers avenue for improving the algorithm's effectiveness and performance. This consideration aligns the recognition in the code that there are few potential areas for further research and refinements. Thank you guys.